Hi, I'm Adam Brindell. I work as a consultant and instructor on data engineering and machine learning, and I wanted to take a few minutes today to demo an exciting new library that provides a SQL front end to Dask. So a lot of people talk about democratizing data and machine learning and AI, and what could be more democratic than SQL? It's been around a really long time. It's really well known by huge numbers of people from many, many different kinds of disciplines, not just in the hardcore data world, but on the business side, analysis, visualization, reporting. So SQL really opens a lot of doors. And so being able to use SQL together with Dask connects some really powerful tooling. Dask is the easiest way to scale up your Python code and your PyData work to much larger clusters and larger data sets. So these fit really, really nicely together. Today I'm demoing this cluster using a tool called Coiled Cloud that provides a great way to create, manage, administer Dask clusters in the cloud. You can try this yourself, so you can run all this code, you can try it yourself, you can sign up for the free beta with a GitHub or Gmail login. And from Coiled, you can create all kinds of clusters. Here's a list of some clusters I've been playing with earlier today. And you can configure and manage them. And you can also launch notebooks to give you a front end for working with your clusters. So what I did to kick off the demo here is I went to Notebooks and clicked on this Launch tile. And that brings me to a Jupyter Lab environment like I've got here. And it actually starts out with this notebook, the one that says Quick Start. And that has some code for spinning up a cluster on Coiled, which looks very much like spinning up a cluster in any other kind of Dask backend. And it has some code for reading parts of the New York City taxicab dataset from Amazon S3 and making a little computation. So I thought, let's start with that, but let me see if I can run it a little bit differently and get SQL running against that data. So I spun up a cluster right before starting the video because it takes a few seconds to get all of these workers deployed, and I didn't want us to have to wait while they all come online. So we've got that ready to roll here, and you can see over on the right hand side I've got the Jupyter Lab extension and dashboards connected, so I can see what's happening inside my cluster. It's kind of idling right now, nothing much else going on. The next thing I did was install Dask+SQL. So this is a code to do that. It's just a conda install. Again, I ran that right before the video because you've probably done some conda installs that they take a good few seconds to sort out dependencies, pull down the relevant packages, and I didn't want to have to do that in real time either. So you can use this notebook, which I'll link to the video, but I'm not going to run this install, the conda install in real time. It just installs with just this one line. Let's get right down to the action here with doing a little bit of work with our cluster and with Dask+SQL, and then maybe we'll talk a little bit about what's going on underneath the hood. So the first chunk of code here is just traditional Dask DataFrame code. It's very similar to the query on the other notebook. The main difference is I removed the chunk size because I'm going to let Dask do a little bit of auto partitioning for me here. And I also got rid of the .persist because for the first part of this demo, I'm not going to cache anything. We're just going to pull all the data brute force over from S3. So this first computation doesn't do anything with SQL. You can see it's regular Dask DataFrame code, and we just want to make sure everything's alive here. So I'm going to run this, and we can see some activity over here in the cluster. If I flip over here to the Dask task stream, we can see we've got quite a lot of cores here. So when the animation syncs up, we should be able to see a lot of things happening here. We can also flip over to the task graph, which shows all of the dependencies in the computation. So here's our task stream, and it looks like it had just finished. And we've got a set of results here, and these represent the average tip for different passenger counts in the taxi rides. So that's what we've got here. And now what we want to do is see if we can bring Dask+SQL into the mix and run some queries against a data set like this. So almost everything runs perfectly out of the box in this environment with Dask SQL. The one thing I had to do was give a little bit of a hint where to find the shared object library that represents the JVM. So there's some code to try and find that. It didn't find it auto-magically in this case, so I just gave a Java home here that points to where that particular value is in this environment. To use Dask SQL, I'm going to import a context object. You can see right down here, and instantiate that. And what I'm going to do is I want to query this data set. And in SQL, data sets need to have some kind of a table name, so I need to give my data frame a table name. So this df, this is a Dask data frame. It's the same one we were playing with just a few cells up above. And you can see what we've got here is metadata, right? We've got some partition information, some information about the tasks that produce this data, and some column names and types here. So this is a lazy data structure by default that allows us to specify what we want, and then we can compute the pieces or the whole thing, you know, if and when we need that. So it doesn't really cost us very much to set this up, since we're not touching much of the actual data. And then we're going to come down here and we're going to assign a table name that matches up against this data frame. So we're going to call it taxi right in here. And then once I've registered this table name, I can then create SQL queries against that table. The first one I'm going to do, again, just kind of a smoke test, is I'm just going to count the rows and see if this works. So I'm going to go C, and remember that's the context object, .SQL. I'll give it a string here, and that's going to give me an object I've called result. And if we inspect result, you can see that it is a Dask data frame. So the result by default here is usually lazy. There's a couple of exceptions that may change in later releases of Dask SQL, but in most cases, and certainly as a goal in the long run, what we want to do is represent the result of one of these queries also as a lazy data structure, and one that we can work with in Dask. So we've got a output here. If we want the actual value, we can go .compute, and we should see some computation happening over here on the right. And it looks like we've got some tasks running here. So counting some rows, and this is CSV data, so there's no easy way to count these rows. You actually have to count them. So that's what's going on over here. We'll get back. I think there's about 8 million rows in this data set. Okay, so let's see, was I right about that? No, I was off by an order of magnitude. There are 84 million rows in the data set. So I'll have to pay a little closer attention next time. Okay, so we've counted the file, and we've managed to run a little bit of SQL and execute it using Dask. So let's go ahead and take a look at that query that we saw earlier. This is average tip grouped by different numbers of passengers. And what we'll do is we'll run it in the regular Dask data frame way, and then we'll run the same thing using the SQL engine. And the purpose here is to see whether we're paying any significant cost and overhead to pre-process this query in SQL. And what we're hoping here is that it doesn't really cost us much anything, because manipulating the query from a string here and then some of the subsequent optimizations and translations of the query, those should be negligible compared to the amount of time that we're spending actually processing data. And that's true for operations like this over any significant amount of data. So we're amortizing a very small SQL cost over a very large data processing cost. So let's just take a look here. How long it takes to compute this. So 24.9 seconds for the regular Dask data frame code. And the next version here uses SQL representing the same exact query. So in SQL, select average of tip amount from taxi group by passenger count. Remember, that produces a Dask data frame. We know that this data frame or series only has about 10 rows, so we can compute it and bring the result up here. And what we're expecting to see, hopefully, is about the same amount of time. So we've got about 24.9 seconds and 24 seconds. If we look over here at the local CPU times, we can also get a sense of what it might have cost us to do that local SQL processing. So it's a little more complicated in this because the stuff in the JVM, but it looks like we're looking at less than 1/10 of a second overhead here. Okay, so let's go and do a couple more fun experiments. Let's try and cache this table. We've got plenty of RAM in our cluster for this, so let's go and cache this. And then we can run queries against the cache data set even faster. So I'm going to run a .persist on this data frame. If you look over in the Dask graph over here, you can see blocks of this data being read in and loaded up into memory. If you wanted to programmatically wait for this to be finished, we can use a distributed .wait. And we can do that over here. So okay, so now we're all set to go. And we're going to go and give a name to the cached version of this. So when we did our persist, we assigned the result to DFP. And here we're going to call DFP taxi cached. And we'll go and count that just to make sure everything is alive again and running nice and quick. Okay, so that count came back really quickly. Let's go ahead and run the average tip query again, this time out of memory, and see how long it takes. So what did it take? 24 seconds or so before. Hopefully it'll be a little bit quicker this time. So yeah, we're getting results back in about 2 seconds this time. So we got a pretty nice speed up. We can also use some built-in expressions. So for example, there are operations like floor built into Dask+SQL. Here I'm just not hitting any data structure with this. I've just run a select floor on a constant in this line of code just so we can see that it works. Floor of 3.14 is 3.0. Once we see that that works, we could try something like apply floor to the trip distance to discretize the distance of these cab rides. And then we can do things like group by distance and maybe look at some data over different trip lengths. So in this case, I'm pulling floor of trip distance as dist, the average fare amount as fare, and the count as trip count. And I'm doing this for each of the discretized trip distances, and I'm doing that between 0 and 50. So I put a % time there just so we can see how long this takes. And it looks like in about 3 seconds we've got some data back. For each distance we can see the cost and the number of trips at that distance. The last thing I wanted to try here was running a report like that and immediately plotting it. So when we have small data structures like this 50-row table here, we can safely compute those or bring those back to our local process. If we had any kind of larger data set, we would not want to do that, right? We'd want to write that into some stable storage somewhere else or leave it out in the cluster. But for something like this, it's small, so we can go ahead and materialize this locally, and it will come back as a pandas data frame. So here I'm running the same query. The .compute gets me a local pandas data frame, and then I'm doing a .plot on that pandas data frame just to compare distance and fare. I have a line here that installs matplotlib because in this particular software configuration I didn't already have that in there. I'm not going to run that now because I already set that up, but I've put it in the notebook so you can try it if you don't have matplotlib in your environment or if you're running it up here in Coiled Cloud. And so pretty quickly we get back a nice plot that shows fare versus distance. And I guess the interesting pieces in here are where this departs from being linear and the slope changes. I guess that involves maybe some tunnels, bridges, or airport trips, something like that. But in any case, we're here to talk about technology more so than New York City cab rides. So I'll let maybe other folks analyze what's going on with the fare and distance. Maybe we'll talk a little bit more about what's going on in this environment beyond Python and Dask, so focusing in on Dask+SQL. So this is the doc page for Dask+SQL. It's a relatively young project. It's just a few months old and had its first official release very recently. And the idea of Dask+SQL is to leverage an existing really strong library for working with relational queries, and then provide the glue that translates those queries into Dask operations. So this is the GitHub page for Dask+SQL. And Dask+SQL, for the actual relational processing under the hood, relies on Apache Calcite. So I'll link all of these in the notes to the video. Apache Calcite has been around for several years. It's a pretty well-established piece of code. Like I sort of hinted at earlier with the whole JVM integration, Calcite is a Java-based project. So there's a number of Python projects that use Calcite, and they have to kind of grab a hold of the JVM shared library in order to make that work. Calcite handles the SQL parsing and relational algebra stuff. So what is that? If you've played around with databases before, you may be familiar with the idea that, at least in the relational database world, the model is that we have a set of objects and operators that we can apply to those objects, and that allows us to represent all of our queries in a kind of a uniform way, as well as establishing formally and mathematically that different queries are actually equivalent. And that allows us to create optimizations. Now luckily, in this case, we don't have to do the optimizations. There is an optimization engine built into Calcite that does quite a bit, and you can also extend it yourself. So that can be extended, and that handles parsing the SQL and manipulating these trees of query operators. So if Calcite is doing all that, where does Dask+SQL come in? Well, the output, in this case, from Calcite, is going to be a collection of operators. And what we want to do is convert those operators into a version that works with Dask. Calcite gives us a representation of our optimized query as a tree of logical operators, and Dask+SQL converts those into kind of an alternative flavor of logical operators, basically the Dask flavor of those. So it's almost like a particular implementation of an abstract logical operator. And then eventually, these have to become physical implementations that can actually work with the data. I recommend checking this out. There's a lot of SQL that's supported. There's also some that's not supported yet. So if you want a fun project to contribute to, maybe filling in some pieces here might be an opportunity. There's also support for running essentially a database server. So there's a Presto protocol server today. Calcite has support for JDBC, so I think with some glue that could potentially work. And that allows you to take tools that don't know anything except how to talk to databases. For example, reporting tools or visualization tools like Tableau. And theoretically, those could then talk to Dask+SQL and use your Dask cluster to compute results. So there's a lot of pieces that can really click together with this infrastructure. So I'll let you take a look at the docs. And to wrap up here, I just want to thank everyone for taking a little bit of time to check this stuff out. I think this is a really exciting development, expanding the power of Python and PyData in lots of different dimensions, from things like Coiled Cloud that make it easy to scale up and run this stuff on the cloud using really nice Python tools and Python APIs, and then Dask+SQL bringing all of the SQL world into it. I also want to have a quick shout out to my data engineering and consulting friend Jacek Laskowski, who inspired this video with his kind message on Twitter. And I hope this is useful. Thanks for watching.